So when you've got that salt bridge, or you've got some sort of interaction between one part of a cell and another part of a cell, you will oftentimes build up charge. And if you are building up charge, you're going to have a little bit of a potential that builds up at that junction. So we're going to look at what happens at these interfaces within our electrochemical cells, whether they be for measurement or just in general. All right. So a junction potential is the voltage difference present at the interface between two dissimilar electrolyte solutions. So electric junction potentials develop because oppositely charged ions are going to have different mobilities. So, for example, chloride ions will diffuse faster into water than sodium ions, causing charge separation at the boundary between a sodium chloride salt bridge and water. So here's a picture of our salt bridge. Right? It's got sodium chloride over here, and it's got water over here. And as you allow things to progress, because you've got a region that is sodium ions where they're going to move faster, or sorry, they're going to move slower than the chloride ions. Those chloride ions are able to move a little bit faster than the sodiums do. So the sodiums are left behind, the chlorines move faster. Now you've got things that are relatively higher concentration in chlorine than they are in sodium. Well, now I've got plus charges on one side, I've got minus charges on the other. I have built up a potential difference at this chemical interface because of relative ion mobilities. Right? So my chlorine goes fast, my sodium goes slower. I'm going to end up with a potential difference. This junction potential puts a fundamental limit on the accuracy of direct potentiometric measurements because usually we don't know the size of that junction potential. Right? So this is a source of uncertainty in our measurement. If we know what those are, it could be systematic. Right? We do a really good study and we know what our mobility of sodium and chlorine is at particular ionic strength. In particular saturated solutions and in pure water, we might be able to do that as a systematic error. But most of the time, because we don't know what our concentrations are and what they are at this potential, like it's also going to matter how long you've been running this cell, right? If you give these chlorines lots of time to separate from those sodiums, that junction potential is going to be different than if you just turned your cell on and took an immediate measurement. So we do need to account for those, right? So our overall cell potential is going to be our indicated, right? That's our right-hand side. That's the one we're making our measurement of, minus our reference. And then we're going to add in the junction potential as well. Okay. We do know some things about some of the mobilities of ions in water at 25 degrees C. KCl salt bridges are oftentimes used because the mobility of the potassium and the chloride ions are relatively close to each other, 7 times 10 to the minus 8 meters squared per second per volt. Right? So they're pretty similar, right? Which means you're not going to get nearly as much of a difference, which means you're going to have a small junction potential. Now, something like hydrogen and hydroxide over here, those are going to have really big junction potentials. So we don't want to make something with hydrogen or hydroxide as part of our salt bridge. Right? We want to try to get these pairs matched as close as we can. All right. We can estimate those. So if I've got a 1 molar sodium chloride, potassium chloride salt bridge, that potential is going to be about 6.4 millivolts. So we're going to apply that as a correction factor to our measure cell if we want to find out the potential of our indicated. Right? So we're just going to adjust things by this little bit over here. Right? A positive sign means that the right side of the junction potential becomes more positive with respect to the left-hand side. All right, so example. I got a 0.1 molar sodium chloride solution placed in contact with 0.1 molar sodium nitrate solution. Which side of the junction is going to be positive? All right, so we got a sodium nitrate solution. We got a sodium chloride solution. Which side is going to be positive? Well, we have to look at which way those ions are going to migrate and which ones are going to migrate faster. So our 4 guys that we need to worry about are going to be Sodium here, right? 5.19 times 10 to the minus 8. We're going to need to worry about chloride, 7.9 times 10 to the minus 8. Nitrate, 7.4 times 10 to the minus 8. So we would expect our two sodiums to kind of do the same thing. So we're really looking at what's the difference between our chloride and our nitrate. Right. So because the sodium is equal on both sides, there is no net diffusion of the sodium across the junction. However, chloride diffuses into the nitrate, and nitrate is going to diffuse into the sodium chloride. Now you've got your peanut butter in my chocolate, and your chocolate in my peanut butter. The mobility of the chloride is greater than that of the nitrate, so the NaCl region will be depleted of chloride faster than the nitrate region will be depleted of nitrate. The sodium chloride side will become positive because its negative charge is moved more over into that right-hand side. The nitrate is moving over towards that left-hand side, but not as fast. So this side is going to build up more negative charge, and that side is not going to get as much negative charge from the nitrates, meaning this side is going to be disproportionately a little bit more positive, and this side will be a little bit more negative. Right. So test yourself. Which side of a sodium chloride and lithium chloride junction will be positive? Here, you're going to be keeping the chlorides constant, and you're going to look at the difference between the sodiums and the lithiums. The lithium is going to move at 4.01 times 10 to the minus 8, and the sodium is going to be 5.19. So which one is moving faster? If you're moving that positive charge, what's going to be left behind? Where's that positive charge going to build up? Ionic liquid-based salt bridges have a smaller junction potential. Salt bridges filled with appropriately chosen ionic liquids are going to exhibit lower junction potentials and are going to give you more accurate potentiometric measurements. So if your two half cells are connected by some ionic liquid instead of a salt bridge that is literally made out of salt, then you're going to have less of this correction factor to worry about. Right? So why is this an issue, or why is it smaller? So here's an example of an ionic liquid. Right? It is this sulfur fluorocarbon guy. It's got a bunch of carbons and sulfates, and it's got this minus charge on it. Right? And over here you've got this bulky group over here and a bunch of R's. So these things are not going to be terribly mobile. Right? They're big and bulky, unlike something like sodium, which is tiny and fast. They still have a minus charge and a plus charge, so this liquid is going to be ionic. Right? It's got charges that can move around, but because they're big and bulky, it's not going to move. If it's not going to move, it's not going to separate. If it's not going to separate, it's not going to build up that potential. And synthetic tuning enables the cation and anion mobilities to be matched within 3%. So you can, if you've got this guy over here and you know how fast it's able to move, well, you can change these R groups, right? Make them bulkier or smaller, depending on whether you want it to go faster or slower. A salt bridge filled with an ionic liquid can have junction potentials as low as 0.1 millivolts, which is plenty within our ability of the voltmeters that we used in lab to make a measurement. Porous glass plugs are often used in salt bridges. What's going to be the reason for that is that they're going to keep most of the salt in the salt bridge. So if we made a salt bridge where it was just a piece of string soaked in salt, or if we had some jello that was holding our salt, we can have a pretty large movement of those ions. A lot of our salt can actually leach out of those. Putting that through a porous material is going to allow the ions to move, but it's going to keep most of our stuff on the inside. And we've got two different size regimes for that. We've got what are called microporous and nanoporous. The nanoporous glass plugs are going to have pores, which are holes in the glass, that are going to be between 4 and 20 nanometers in diameter. They're less robust, they're more fragile, you can scratch them up real easy, they can get clogged, they can get junked up. It's more selective obstructions. It's going to allow one ion to pass, but not another. So here, this chloride is too big to fit through, but that tiny little sodium can make its way through. So it's more selective, but it's got a higher chance of junction potential instability. So like you could wreck that pretty easy. Microporous glass plugs, the pores are 100 to 3,000 nanometers in diameter, so 3 microns. They're best for most measurements. They're more robust. They've got larger pores, so they're going to have fewer selective obstructions. But because it's bigger and less fragile, you're going to end up with a more stable reading. So most of the time, you're going to end up with a microporous glass plug. Now, you might have wondered when it said selective obstructions, and you see this guy is rejecting chlorine but allowing sodium to go through, you're doing a physical separation process. And you might say, hey, is that something that we can exploit and take advantage of to make a selective surface? And the answer is yes. Yes, we can.